My name is Johan Sandquist, and I'm the CEO at WireFlow. And I will walk you through the project we did together, and I will also talk a little bit about measurement techniques on batteries. So, but first, let me introduce WireFlow. We were founded in 2011, and we have our main quarters here in Gothenburg. We also have small offices in Helsingborg and Karlstad. And we are focused on the NI platforms, both hardware and software. We are a NI Silver Alliance partner, and mainly our main focus is RT and FPGA programming. And you will see some things about that later. So we have two business areas within WireFlow. We have a project area where we work, where we do our own products, which fit into the National Instruments ecosystem, we call it. So we have something we call the security suite, where we have, here you can see a collection of the products we have, fingerprint readers and USB security dongles to keep your LabVIEW code safe. We also do C-series modules for CompactRIO and CompactAC. Our own that complement the NI portfolio. They have a lot of modules, but some they don't. So we complement them. We also do some LabVIEW toolkits that we market and sell on LabVIEW Tools Network. So, so that's kind of the first area of business we work in. The second is services. And here we can see, for example, custom electronics. So we are a product company, but we also do special products for customers that have special needs. So then we take the requirements from the customer, we make the electronics, manufacture it, and even sometimes we have it in stock and sell it to them when they need. We have the integration services, which this product I will talk about together with Michael Power and Anders is a perfect example of, where we did most of the job at our office with feedback from Michael Power, of course. And we have some traditional consulting. So, okay. Before we dive into the project, let's talk a little bit about measurement techniques. For those of you who have worked with batteries before, this would be basic. But if you have not worked with batteries, there are some things you should think about before making an automatic test system. So most of you own your own voltmeter at work. So if you have a battery stack, you can take that and go and measure any battery without a problem. But when you want to create an automatic test system, you want to connect every battery cell in the system, and that's when it gets a little bit more complicated. So there are a couple of things that I think that I would like to share with you. When you look at modules, analog input modules, they are often called single-ended modules or differential modules, depending on how they work. So if you want to buy a cheap module with high channel count, they will probably be single-ended. And a single-ended module has a shared ground. So if you would connect a module like this here, let's see, you connect the ground here, and then you start to add channel 1 here, channel 2 here. The first measurement would be 3.7, fine. The second would be not be 3.7 because you would measure this in series. So as I say here, you can do max 2 standard cells. The third will go over most of the analog input modules that you can buy because the range is 0 to 10 volts. So Most of the time, a single-ended module is a very bad choice for a battery testing system. So what can we do with this? Well, you can go for a differential module that doesn't have a common ground. And in that way, you can measure all the batteries you want. But then another thing comes in mind, and that is isolation. Some of these systems that I had talked to people here today, and they say that they build systems up to 900 volts and stuff like that. Then if you look at a normal analog input board, they have channel-to-channel or channel-to-ground isolation for most of them 250 volts. So if you connect that to a 900-volt battery, it would not be that nice, actually. So it will destroy your equipment. So you have to know what are you measuring on, and what kind of isolation does the board have that you want to use. And I think that the final tip is to actually use a device that is made for measuring on battery cells. There are battery stacks modules that are made explicitly for this with a much higher isolation, and that takes care of all the issues. And they are a lot cheaper most of the times than working with a differential standard analog input. So let's dive into the project we made with micropower. Let's do some recap of the requirements. So micropower wanted a rig that could cycle. That means we would charge the battery system and then discharge it, and we would do that for, let's say, a year or more without interfering with it. So that was the main challenge, and so we had to do a robust kind of implementation that could handle that, and also that would create a lot of data, because we should log all the external buses to the battery system as well as internal, and we will also monitor individual cell temperatures and cell voltages for this system. So it will be a huge amount of data. So it's terabytes of data. As Anders also talked about, they wanted to add an extra safety layer around their own basic systems. So they are safe in their way, but we added that for all the external equipment as well. So, and they wanted the system to be able to support all their versions. As Anders shown earlier, they have a lot of different versions of batteries, so the system should be able to support all of them. And even they wanted to have some headroom for future expansion as well. So that was kind of the high-level requirement. So let's look at the solution we made. So the system has, I think, three main components. Here you can see two of them. It's the charger and the electronic load. So that's kind of the heart of the system. It makes Anders happy because it can charge the system, the battery, and it can discharge it. But and for the charger, it was pretty easy to choose the brand. Anders handed over a charger for us that they had chosen that they would fit this perfectly. And we chose an electronic load from iTech to do the load part. But there is a third component missing, and that is a system that controls this. And in this case, we chose a CompactRIO system from NI. And it has a lot of benefits. But for those of you that don't know the CompactRIO platform, it's a real-time operating system running on that, and it's connected to an FPGA. So And then you have modules that you can see in the bottom that you attach into the chassis to get the I/O or bus connections that you want. And NI has a lot of different I/O modules. For this particular case, we chose a 9035. It's an 8-slot chassis. It's the one that you can see on the picture, but with a lot of different modules in it. And that's because of a couple of things. It gave us RS485, which is one of the buses we should actually measure. And it has an SD card slot, and we used that as a buffer for the logging part. I'll come back to that later. It has USB support as well, host, so we could use that to monitor and execute commands on the iTech electronic load. So the CompactRIO actually do the switching and control that. So that were the main reasons. There are other components as well for that. And it has 8 slots. So we only needed 5 modules, so we would have 3 spare slots for future expansion as well. And after that, we had to add some extra modules to get the full functionality. So we had 2 CAN modules to get, because the battery system has 2 CAN buses. We had a digital I/O 24 volts module, a thermocouple module to measure the individual cell temperatures, and to measure the individual cell voltages. We had a battery stack module actually made by us. It's a 24-channel 5 volts battery stack module, so perfect for this kind of application. So after this was done, we talk a little bit. I should talk a little bit more about the software and the other things that came around the hardware. So as I said, it's a lot of data. So we should run this for years. And to do that, we figured out that CompactRIO doesn't have enough data to store all that logging. So we have to use a server on the network. But Micropower also had a requirement that we can't lose any data. So even if the servers go down, we shouldn't lose data. So how do we do that? Well, in this case, we use the SD card slot. So the SD card slot we use as a buffer for the measurements. So the measurements go onto the SD card first, and after that, it tries to connect to the server. If it's available, it will put the files on the server, and if it's not, it will keep it on the SD card for as long as the server doesn't respond. So the IT department has some time to upgrade to the latest version of Windows or whatever. So the SD card is big enough to hold a couple of days of data, so they should have enough time to manage the systems. For this as well, we made a standalone user interface that you can see a picture of here as well. In this, you can connect to the system from a desk anywhere at the office, because this system should be, as Anders said, would run unattended for a long period of time, and you don't want to go there. Perhaps it's in the lab, tucked away somewhere. So this can connect through the network, and you can see the status of the system and what kind of things is going on right now. And you can see live data coming through as well. And you can follow a specific parameter if you want to do that as well. And in this system, you can also go in. I haven't talked about the different settings you can do, but the operator can set up different scenarios for the charge and discharging based on SOC values. So, and you can do subsets of those as well. And if you want to change things during this 1 year period, you can do that as well. So you can go into this system or this graphical user interface, and you can change the setup that you want to have and commit it to the system, and it will change the values for the different runs later on. And coming back to that unattended thing again, so we also set up a service inside this that could send mails to any user that wanted to subscribe. So you can, for example, set up a status mail that is sent out once a day or once a week or something like that to see that the system actually is running. So that's configurable with this system as well. And finally, they wanted to have that extra layer of safety. So what we did, so this system, I will show you a picture later, is actually a 19-inch rack. So what we did was we added a fire alarm inside it to detect if there was smoke coming out from the system. And we hooked that one up to the CompactRIO, a module inside there, to monitor the fire alarm. We also measure the cell voltages and cell temperatures, and we have set up some criteria for when the system will go into alarm state when it gets too hot or the cell voltages go too high or too low. That could damage them and also create emergency states. So that's configurable by the user as well. And all of that was actually put into the FPGA of the system. And an FPGA is very good because it's isolated from the rest of the system in a good way. And it's really quick, so we can have a quick response when something is out of order. So what the FPGA then does, if an alarm state arrives, it's actually to disconnect everything from each other. So the battery is disconnected from the battery system, and the charger is disconnected, and as well the three-phase into the rack is actually disconnected as well. So it will be powerless. And before we do that, or at the same time, an email will go to the operator that an alarm state is actually happening right now, so they can go down and take care of it. So the result is this. You can see it's a 19-inch rack. You can't see the door, but it's as well with a door that you can lock to not let everyone inside the cabinet. And at the bottom you can see the electronic load, and you have the charger at the top and the CompactRIO in the middle. And then a lot of relays and stuff like that. So that's pretty much it.